good enough for us to hire people that get those degrees other places and then come here and get jobs and then we reach all this system.
No, stop blinking. We're on. We're live. So, welcome back. Football hasn't quite started yet, so we're going to be continuing our discussion on Fourier transforms. Last time we looked at the definition of Fourier transforms. We grew out of an observation of Fourier series. We used the Riemann sum principles of continuum to get us a working definition of a Fourier transform pair, the ability to move back and forth between time and frequency. So in this case, we're going from the time information. The integration gets rid of the time, and converts it only to frequency. In this case, we have a frequency representation of the information in the signal, and we go frequency, defrequency across a full range, and that gets us an expression that's time, the time representation of the information in the signal. So here's your Fourier transform pairs, and we illustrated that a little bit with one example, a pulse. We like pulses. We're going to use a lot of them in this class in various ways. Here's a pulse in time. And we learned that it Fourier transforms to a sin x over x or a sinc function in the frequency domain. And I don't think I made too many mistakes on this, and so we can keep track of factors of 2s and pi's and so on and so forth. I made the observation with the Fourier series, and I'll make it again with this, that a symmetric pulse here gives us a symmetric pulse in here, real and real as well. So definite parity, real pulse, and the parity is preserved across the transform. And there's a really rough sketch on it, although I know by now we've had an hour for lunch, so I know by now most of you guys have been plotting that in between bites of pizza. That's a joke. So there's a couple of now we get to a little bit of boring bookkeeping for a few moments, just to go back over some of the properties of Fourier transforms, and you've seen this before, so it is a little bit boring, but I think it is something that we should go back in and just remind ourselves of various properties of the Fourier transform. And I think just by reminding us, we'll be using these, and we'll be using not just one at a time, but in combinations. And so, again, having them at the tips of our fingers will be helpful. And the first one that's kind of odd is linearity. The Fourier transform is a linear transform in the same sense that we talked about, linearity in terms of systems, linear systems. Well, linearity is also the Fourier transform itself is a linear transform. Now, what that means, and this is exactly the same definition that we used for linear systems. If I have a Fourier transform pair x of t, and that Fourier transforms to x1 of omega, so I have x1 of t and I have x1 of omega. And then let me also suggest that I have a Fourier transform pair that's x2 of t and x2 of omega. Then by linearity, a linear combination of x1 and x2 will give me the same linear combination of x1 of omega and x2 of omega. And again, that's a consequence of the fact that we have a given amount of information in x1, and we're representing that information in the time domain here and the frequency domain here. We have a certain amount of information in x2, and we're representing the time domain here and the frequency domain here. So if I weight and add, W-E-I-G-H-T, weight and add the information here and here, then that same weighted in superposition of information should be expressible in the frequency domain. So there's a physical reason why the Fourier transform is a linear transform. And mathematically, I'll write A, x1 of t, so A is the weight, W-E-I-G-H-T, plus B, x2 of t. There's my superposition. There's my weighted average, my weighted superposition. 3 parts this, 1 part that. 99 parts this, 1 part that. That's how you construct new entities all the time. This Fourier transforms to A x1 of omega plus B x2 of omega. And I'm old and my memory is going, but I think that these things are part of homework problems. The proof of these is really straightforward. Don't be stressed out about the proof. All you do is you write down the Fourier transform pair for x1 and x2. You write it down for x1 to x1 omega, x2 to x2 omega. You write it down for this. You break your integral into two pieces. You pull the constants through the integral and make the identification, and you're home free within 3 lines of code, 3 lines of proof. So I'll leave that as an exercise to you guys, but also with a little bit of hand-holding that the proof is really easy, and doing the proofs, and I think I've assigned it in a homework problem, but doing it will help reinforce it from a memory perspective as well. And I don't mean for you to memorize them. What I mean for you to is so familiar with them that you can use them, not just recite them. Reciting them is rather boring and doesn't really constitute, a usefulness. But if you can use them, if you can, so comfortable with them that you can deploy them and use them as you need, that's where we want to be on these. Okay? All right. 2. Conjugate symmetry, and what conjugate evokes. What conjugate evokes is that we have a complex transformation. We have an e to the I omega t in there, or an e to the j omega t as our kernel, Kernal. And so what that means is automatically when we do those Fourier transform pairs, we introduce the possibility of a real part and an imaginary part in the frequency space. So even if I start with a real function in the time domain, I have a better than even chance of getting a complex function in the Fourier space. And the reason for that is exactly what we've looked at in the Fourier series. Phase is important, and j, the square root of minus 1, j is the index that we use to denote a relative phase relationship. So real parts versus imaginary parts are what we come out are hidden in that word conjugate. And then symmetry is a balancing, a parity, some sort of operation that preserves a structure. And so in this case, conjugate symmetry is supposing I have a real signal, and we probably will. It's hard to imagine a voltage that can't be written as a real voltage, cosine of omega t plus phi plus theta, for example. So there's no reason why x of t shouldn't be real in a real physical system. Well, if that's the case, then x of minus omega, so what happens in the negative frequency range? What happens to the negative frequency range? That's going to equal x complex conjugate of omega. And so that's a little shortcut. That's a little shortcut for figuring out Fourier transform pairs if we have a real part. This is a little vague and a little bit fluffy, but later on down the line when we look at single sideband and QAM for amplitude modulation, ways to double the utility of a channel, double the usefulness of a communication link, then these kinds of results will be really interesting. And it turns out that we won't need to be exactly this formal, but I want to start to draw a line from the math to a practical engineering application that we'll get to. I'll say in a few lectures, where a few lectures will be, of course, a few weeks, according to our strange presentation of this course this semester. Okay, we've looked at this one real informally before. Time shifting. What happens if I shift or I delay a pulse or I delay a sinusoid or I delay a signal? What happens if I shift it over in time? Well, I have x of t. So now I shift it in time, x of t minus t naught. And So instead of x of omega, what I have is an e to the minus j omega t naught times x of omega. So I have this extra little factor in here. This phase delay factor in here that multiplies through the Fourier transform, the original Fourier transform pair. So in the past, this has been these properties, and this in particular have been given to you on how do you extend to the table of Fourier transform pairs that you have. If you're given a cosine, how do you calculate the Fourier transform of a sine? If you're given a cosine, how do you Fourier transform a cosine plus some small phase shift? And so that's very much the spirit of what this is. But it also has other ramifications as well, as we've seen. This is a delay element, and so what I do is I take the signal in the frequency domain and I multiply it by a delay block to illustrate what that delay is. And remember, delays are very important because they're one of the three major parts of a filter. Right? A filter will take a signal, you'll split it up into components, it'll do relative delays of those components, it'll weight them, W-E-I-G-H-T, and then it'll put them back together. And so we want to be able to describe filters, and this is an important piece of the puzzle for how filters operate. Okay? So time shifting is yet another property of the Fourier transform. If someone brought the Lottie book, there's the table of Fourier transform pairs, and then there's the table of properties. I think it's 3.1 and 3.2. Table 3.1 and 3.2. So those are good reference lists for these things. It also sort of calibrates you where we are in the textbook at this time. We spent a lot of time talking about differentiation. We know it's one of our favorite operations to do to a function. We also started to look at that in the context of what different types of filters are. So differentiation, I might remind you, I won't be able to convince you right here and now, but I might be able to. Hang on. Differentiation is a what do we call it? A low pass or a high pass filter? Yeah. Well, let's take a look at it. Why not? There's my Fourier transform. There's my property. There's the property of differentiation. And it seems to me if I look at that, then here's my x of t and here's my x of omega. The Fourier transform of the differential operator, if that goes to that, and that's d by dt, well, it seems to me that j omega. It seems to me that j omega is the Fourier transform of the operator. Does that sound reasonable to you? Mm-hmm. Okay, so let's see what that means. I want to look at the magnitude of that. So the magnitude of j omega is going to be the real part squared plus the imaginary part squared, square rooted. Does that sound right to you guys? What's the real part of that? 0. Yell it out. You're right. Don't be shy. So that's going to be a 0 squared. And what's the imaginary part of that? Omega. So that's going to be an omega squared. I add them together. So that's going to equal omega. And let me plot that. So this is the magnitude of j omega, that transfer function, and it looks like it does that. Oops, there you go. Looks like it does that. Even better. And so if this is my Bode plot, if that's my omega, I ask you a question: which is favored more on that graph? Is it the high frequencies or the low frequencies? So this is a high pass filter, right? Nothing too fancy there. Okay. So yet another indication of what I've been talking to you about, low pass filters versus high pass filters. I hope you're either getting that concept, getting comfortable with the concept, or at least so comfortable that you're bored. So now you've got several articles here that all are pointing towards the interpretation that I'm kind of belaboring, I suppose. Okay. All right. So the property of differentiation. For B, integration. So the integral of minus infinity to t, x of tau d tau. That Fourier transforms to 1 over j omega, x of omega. And there's a funny extra term in there. So that's sort of what we think about. And that certainly gets you from there to there. But we have this lower limit of integration. And that lower limit of integration is a constant of integration. It represents the amount of power that existed in the system, or the amount of energy, or amount of signal that existed in the system at some very, very recent, very, very, very long time ago. So this is my constant of integration. So I've got to account for that. And the funny extra term is that spike of frequency, that spike of DC, that spike of DC signal. Okay, so this guy here is the constant of integration. Okay. And so I most of us will remember this, and then if we remember that we're doing an integral and we have a constant of integration, then at least we'll remember to add an extra term in there and then to figure out what that is or look it up. Okay, so it's easy to forget. Well, again, let's ignore the constant of integration for just a second, and let's look at what this operator means. There's 1 over j omega. And again, did I say an integration was a low-pass filter or a high-pass filter? Because the other one was a high-pass? So I want to know 1 over j omega here. So I can do this in a variety of ways. I can have minus j over omega. Right? And so I want the magnitude of that, so that's going to equal the square root of the real part is what? The real part is 0. The imaginary part is 1 over omega squared. It's actually minus 1 over omega, but when I square it, I'm okay with that. And so this is equal to 1 over omega. And there's my 1 over omega curve for the magnitude of 1 over j omega. And does that look like a low-pass filter or a high-pass filter? Funny-looking low-pass filter. Low-pass filter, the low frequencies are favored more than the high frequencies. Okay, so you've got this issue of what's going on here. You know, the singularity should give you heartburn. Maybe the constant of integration will fix that. I don't mean this to be anything like a proof. I just mean it to be sort of an illustration of the general shape of the function or the filter response. Okay. So yes, yet again we have our intuition is pointing our way for how we interpret differentiation integration. Now, let me go back to differentiation here. Okay, let me go back to differentiation here. We use this property an awful lot. We use that property an awful lot when we talk about differential equations. So the differentiation property and differential property. If I've got a dx dt, well, that Fourier transforms to j omega x of omega. And so if I have a Fourier transform, d2x dt squared plus the square root of k over m, I think that's right, x of t, yeah, that's probably right, then, or actually, hang on, no square root. That's for a spring mass system. Then that's going to Fourier transform to j of omega squared x plus k over m capital X of omega. That's one way of converting a differential equation into an algebraic equation. And we can also get the same thing by substituting x of t equals e to the j omega t. So the Fourier transforming of differential equations is the same as substituting the e to the j omega t kernel into the equations. Okay? So those are two different ways of looking at the same thing. Okay? So I want to be inclusive about what we Fourier transform. We can Fourier transform signals. We can Fourier transform components. We can Fourier transform systems. We can Fourier transform now equations, differential equations, with this differentiation property. And there's the turn the crank mechanics of applying that property, and then the rationale for doing that, or another thing that substantiates that, is that it's the same thing as substituting in for guessing a certain solution. And the thing we substitute in is the kernel. It's the essence of the Fourier transformation. So not a surprise that it works that way. Okay. So again, your past has been very interesting. You've taken a differential equation course and you learn to guess a solution. You take a networks course or other course and you learn to Fourier transform the equation. And then use lumped impedances and so on. And then you take a signals and systems course and you learn the differentiation property. And my goal is to sort of tie each of those views together into a single line. Okay, so it's how you get there doesn't matter. You're doing the same operation. Okay? So holistic looking. We have to look holistically at all this stuff. And when we do so, I'll tell you, it makes our life so much easier because you're not juggling different perspectives. You now have a unified view of all the mathematics that you've been introduced to in a variety of different ways. It must be very frustrating for you to realize that we've wasted your time so many different ways. Like, here's how we do it in this class. Here's how we do it in this class. Well, they all are doing the same thing, slightly different ways. Slightly different, perspectives, but getting you to the same area. Look at it this way. There's a lot of nonlinear systems in this class, so it's good to button up the boring linear stuff quickly and easily. Okay? Back to the properties. Time and frequency scaling. This goes to the pulse bandwidth product that we looked at for the square pulse sinc function. Fourier transform pair, x of t, x of omega. I dilate or contract in the time domain. I do the reverse in the frequency domain. I'm going to limit myself for now for real A's. So if I make this faster in the frequency domain, I make it fatter in the frequency domain. Higher frequencies in the time domain, more frequency content in the frequency domain. Longer pulses in the time domain, less frequency in the frequency domain. And then one thing I didn't, when I waved my hand about that the other day, one of the things that I didn't quite, maybe you caught it, I didn't mention it, maybe you caught it, but remember those triangle pulses that I was making fatter and shorter? I was having different energies associated with those when I clipped them in different ways. And look at what's happening to the energy, or magnitude renormalization. Okay? So there's a magnitude turn in there. If I make the pulse shorter, I have less of it. Unless I make it higher, I have less of it, so therefore I have less of a Fourier transform. Okay? So Fourier transform pairs in your table 3.1, is it? Your table 3.1 goes from, say, the time to the frequency domain, but you could instantly double it by writing down what the time domain is for the frequency result is in the time domain, and then the time result is in the frequency. Let me write it a better way. If I have g of t in the time domain, and I Fourier transform that to f of omega in the frequency domain, then it stands to reason that f of t in the time domain is some relation to g of omega. There's a factor of 2 pi, which comes from our particular definition of what a Fourier transform pair is. And then there's this little minus sign floating around in there. Comes from that e to the I omega t versus e to the minus I omega t. So there's a duality property, and you've just doubled the length of table 3.1. So there's the information in the signal, and the information is the same in the time domain or the frequency domain. The time domain is just a representation of that information, and the frequency domain is just a representation of that information. Well, there's another attribute, and that's the energy, and that energy should be the same whether I express it in the time domain or the frequency domain. I put a cup of water into a microwave, and whether I describe the microwave signal that heats up the water as whether I describe that in the time domain or the frequency domain, this is still going to get as hot in the same amount of time, because the microwave doesn't care about time domain versus frequency domain. So that's sort of a piercing glimpse into the obvious, but to write this down, here's the expression for the energy in the time domain, and here's the expression for the energy in the frequency domain, and I've got a little factor of 2 pi to take care of. Okay? If I flip these too fast, just let me know. Get myself into trouble by limiting my real estate too much. Oh well, I'll live dangerously. Here's your favorite, the convolution property. Right underneath it is something that you just passed over and never gave it a second thought, which was the modulation property. Right? So in signals and systems, you spent an awful lot of time on the convolution property, and you walked away saying, boy, that was great. And right underneath it, which you read and noticed and was remarked upon in class, but certainly not celebrated, was this modulation property. And if this is, I'll oversimplify to make a point, if this is signals and systems, then this is comm systems. Okay? I.e. amplitude modulation, i.e. frequency modulation, i.e. pulse code modulation. In other words, all those use of the words modulation, particularly in amplitude modulation, has to do with this modulation property. And we'll look at that probably in the next section, the next little lecture that we give, the one starting at 2:30. Yeah, we'll look at that later. So let's write down what these guys are. You know this. You probably there are probably people in your class that have this as body art. That's a joke. I neither condone nor discriminate against that. If I have a convolution in the time domain, y of t is equal to h of t convoluted with x of t. And now you should be just happy as the dickens to do those kinds of calculations, because I spent all of 40 minutes on it. And you're much more comfortable with that, right? I hope so, actually. I hope so. But that and in the frequency domain, I Fourier transform y of t and I get y of omega. I Fourier transform the impulse response, or h of t, and I get h of omega. And I Fourier transform x of t, and I get x of omega. And this convolution integral becomes a product in the frequency domain. And that's really nice. That's really nice because it's really nice because you now have a nice clean product of things. But I will also argue that if you want to get back to the time domain, you have to inverse Fourier transform this guy. Okay? So if you Fourier transform this, Fourier transform that, to get h of omega and x of omega, you multiply them together, you've got y of omega, but if somebody wants y of t, you still have to Fourier transform it back. And that's something that you didn't do very much of. Right? You sort of left everything as y of omega. So you kind of got away with something, which is fine, but you should know that you got away with it. Okay? Now, the reason I'm drawing this on the same paper, and by the way, this comes right after the duality property, right? So the reason I'm drawing this cramped on one piece of paper is this. If I've got r of t, which is equal to the product, and we have to spend a lot of time talking about what we mean by a product of two time signals. I'll use words like collision, blending, mixing of two pieces of two informations. So mathematically, I'm talking about a product of these two functions, of these two signals. Intuitively, I look at a mixing of one to the other, a blending of one to the other, a collision of one with the other. The information of one collides with the information of another. The information of one blends or mixes with the information of the other. Those are words that mean multiplication in this context. Okay? So P of t is modulated by S of t. P of t is modulated by S of t. Again, we're going into COM systems and we're going into modulation pretty soon. And so we want to look at that. Well, okay, so you like multiplication, but if you want to do this in the frequency domain, the duality property tells me that I need to convolute in the frequency domain. So again, if you thought you were ducking the issue of convolution in signals and systems because you Fourier transformed it to the frequency domain, well, what are you going to do here? Right? What are you going to do here? Because you want RT in the frequency domain, so you don't escape, unfortunately. There's an extra factor of 2 pi in there. Now I'm being a little bit mean, a little bit snarky about that. The real I've told you this as well. The real thing is you should do what's easiest on both on this side, and sometimes convolution is easier, and you should do what's easier here, and sometimes multiplication is easier, sometimes the convolution is easier. Okay, but again, here filters, here modulators. And in signals and systems, you are fairly focused on filtering, linear time-independent systems, linear time-invariant systems. In a COM system, half of our boxes are going to be filters and half of our boxes are going to have modulators in. And then to invoke Yogi Berra, there's another whole half of boxes out there as well. No one's doing my conservation of probability. Yes, sir?
What is a modulator?
We'll get to that. Absolutely, we'll get to that. The thing that's staring us in the face here, and the thing that we know is that a modulator multiplies two functions together.
And so what we did in signals and systems was kind of
filters.
Filter, like split.
Well, let me add some stuff underneath this. It'll get a little bit cramped, but I think you've seen it before, so it's okay. In signals and systems, you did stuff like this: h of t to y of t. Okay. If I draw this guy here, it seems to me that I have a box with a multiplier in there, and I take s of t, and I take p of t. And out comes r of t equal to s of t multiplied by p of t. Okay? So this is the block diagram for the convolution property, and this is an LTI system, maybe, right? And so this invokes filters. And this product, this multiplication here is, I'm just representing as a little product sign there. And this is called a modulator or a mixer in the parlance of COM systems. Okay? So I hope maybe that helps me. I don't know if that really answers your question, but at least it gives you a picture to go with it. And then on the next class, if I don't run out of time, I'll talk a lot about modulators. And not just kind of this manipulation, but I also have a whole lecture on the architectures of modulators, optical, electronic, and so on. And maybe we'll touch a little bit on that this afternoon, or if not, when I get back. But this is pretty darn core for our COM systems. Okay, as is this. We're not going to get away from filtering. We're just going to use filters in conjunction with this, and a conjunction of and a bunch of other stuff to build up more complicated systems. Okay. Well, let me add a couple of other things on this. In the frequency domain, I have this guy here, and again, y of t is convolution here, and so there's that, and there's that, if you want the mathematical meaning of everything. To me, this whole business of multiplying in the frequency domain, it's not to make our problem easier. It's not to make the problem easier. That's so magical and wonderful about the convolution property. What's really magical and wonderful about this convolution property is I can turn things around. I can write h of omega as y of omega over x of omega. That to me is worth so much more than just saving a little bit of math. Because remember, if I'm going to run out of the math of here and the math of here, and when I do that, I'm just going to go numerical. I'm just going to go to MATLAB. Whether some of us do that for 10% of the problems, and others do that for 30% of the problems, and others do that for 90% of the problems, really doesn't matter. But what's really interesting about this is the output divided by the input. Okay? And so I've turned the problem around from an analysis problem to a design problem. Okay? So here's my analysis problem, and here's my design problem. That's really the most incredible thing about that convolution property to me, is that I can decide what frequency content I want on my output. If I know what my frequency content is on my input, I can adjust h of omega to get me what I want and not what I don't want. Okay, that's really the amazing thing. So this slide here are two of the most important properties that we're going to look at in this class, because it talks about the filtering, which I guarantee is important for communication systems and all systems, instrumentation or robotics or whatever. And then particularly useful in communication systems, but also instrumentation. And I don't know anything about robotics, so I can't say that. But there's a modulation property. Okay, so we have some idea about the mathematics of the filter in the time domain, the mathematics of the filter in the frequency domain. We have some ideas about how to realize what arrangement of R's, C's, how to program a DSP to realize these filters. Okay, and so all that stuff is going to come into play, and all that stuff we're going to have to remind ourselves of. But you know it, you've been introduced to it at least, and you'll get much more comfortable as we work with it more. That's just the nature of things. And you'll surprise yourself on how much you really are comfortable and how much you really know now about them. This is a whole new world. This is equally exciting, equally neat, and equally useful. And so where we are in the course right now is we want to button this up just a little bit. I have one example that I want to spend some time on. I want to spend the rest of the class on this particular period on an example here, and then the next time I want to start with this guy here, and I want to bring you up to speed on that, on the modulation property. Okay, and what that means. Okay, so this is a really nice. I'm going to call your attention of all the properties that we have. The other ones were so useful and so important in just the currency of working with these things. Those are just things we'll use, without thinking about it. But these have real meaning. These two have real fundamental meanings when it comes to designing and laying out and analyzing and designing and implementing these communication systems that we're looking at. And by the way, as I mentioned in the break, the communication systems, it's a really important application. It touches everybody on the planet. And when I say that, I point out that cell phone penetration across the population of the globe is more than electricity penetration across the globe. More people have access to a cell phone than they do electricity. And that's almost impossible if you think about it. But that's true. But it's true. I will argue, I'll stand by the defense that comm systems is an absolutely important, essential part of electrical engineering. But beyond that, we're not just teaching you comm systems, we're teaching you the art of moving a signal through a large number of components and devices and subsystems. Okay? And that's one of the biggest takeaways from this course. And that'll hold you well in instrumentation design, in robotics, in board design, in chip design, in any other system level design. Okay? And so that skill set is something that we'll really want to emphasize. And if you look at it that way, then comm systems is just a means to the end to teach that. Okay? All right. Now, let's see. I cleaned up this little section of notes, which I say that proudly, but I also say it as a warning. I cleaned it up recently, which means I probably introduced a few errors. So stay awake after lunch and try to catch things. Hopefully it won't crash and burn. But let's say example of filtering. And that title doesn't do this justice. That title doesn't do what I'm going to do justice. So I want to say consider a simple RC circuit in several ways. And the RC circuit is something that we've already looked at. But now I'm going to pretend to be a little bit more careful about it. Notice that I'm saying I'm not going to be more careful. I'm just going to pretend to be more careful about it in the description of this. And so here I have here I have a capacitor. Here I have a resistor. And I've got a current that flows through the capacitor. I've got a current that flows through the resistor. So the first thing I'll point out is that I have the current that flows in the capacitor. I think is C dV dt. Oh, let me do this way. 1 differential equation. Okay. So I'm going to take this simple circuit, and I'm going to remind you that we can analyze it by differential equations. Okay. You've done this before. Help me out. Which course have you done it? Which one? ENA? Yeah. Maybe also physics? Yeah. Also physics as a differential equation? Less so. Did you do it as an example in a differential equation class?
Yeah, a little bit.
When you did it, when you did differential equations, did you do spring mass examples or did you do LRC examples? Both?
One example was given.
Okay.
With no intuition, though.
Okay. I like LR. My intuition comes from a spring mass system. I'm a very funny electrical engineer. I start with a spring mass system and then I do the LRC. but it just makes it. But again, everybody's different, and so it's just the way just the shady characters that I hung out with as a undergraduate and a graduate student. Anyway, so I also have a current that flows through the resistance, and I'll call that I sub R. And this is equal to V over R, right? Did I get that right? Phew, that's good. That's good. And then I also know that if I have a current that flows in, then by Kirchhoff's current law, which actually is a law, unlike Kirchhoff's voltage law, which is a horrible abomination of an approximation. I'm not bitter. Kirchhoff's current law is a conservation of charge. And so I can safely say that the current that flows through the capacitor, the current flows through the resistor, is there equal to whatever current that flows in. And all that does is it gives me an excuse to write these guys together into a dV dt plus 1 over RC. V is equal to IN over C. This is volts per time. This is volts, and this is 1 over time. And if you compare that to the original equation of motion for a capacitor, then that's also volts per time in there as well. Okay, so units work out right. Especially with differential equations, I always like to check my units because that oftentimes gives me interpretations of what those constants are. In electromagnetics, when you see a 1 over c squared there, when you see a constant there, it'll look at the units and it'll help you understand what that constant means in terms of speed of light. Second order equation. All right. Here's my differential equation. It is a first order differential equation. It's ordinary, not partial. It's ordinary differential equation in time, first order. It has constant coefficients, and it is forced. Okay, so those are adjectives that I use when I approach a differential equation. When I derive when out of my derivation I pops a differential equation, I stop and I apply adjectives to it to categorize, to think about where exactly it fits into the whole scheme of things. Okay? Where the complexity might live. It's a first order, linear, ordinary differential equation with constant coefficients, and it happens to have a forcing term. And in math class, you're taught to solve the unforced case first, or I think they call it a homogeneous. I think in differential equations they use words like homogeneous, and this would be an inhomogeneous equation because it's forced. That's not the way I use it in electrical engineering. Homogeneous and inhomogeneous has to do with a material property. So I use forced and unforced. I'd make a bad mathematician for many reasons. So my vocabulary shifted over a little bit, but so when I say forced, they say inhomogeneous. Regardless, it's funny. It's kind of funny when a differential equation guy has to solve this equation that's forced. What's the first thing he does? He solves the unforced equation first. I'm remembering a word, trivial solution or particular solution. Yeah. So first I solve not the particular. First I solve the general, and then I solve the particular. So the general is a fancy word for just ignoring this term. And then somehow the particular is something putting that back in. And I'll redraw the circuit like that, and now this input current has to do something. It goes there, and maybe that will start to hint at a connection between what this forcing term is, or the particular solution is, in light of a signals and systems approach to that guy. Okay, I won't satisfy your curiosity completely here. That way, I'll keep you on the edge of your seats. Audience here. Okay. So dV dt plus 1 over RC V is equal to 0. That's the unforced case. Homogeneous equation. Would you say it was the general solution? I'll write it down, and if I'm wrong, I'm blaming you guys. Okay. I remember the terms very vaguely here.
So the solution for that would be the general solution.
Yeah, I wrote down general solution. Here we go. Implies the general solution. That's almost right. Okay, so dV dt plus 1 over RC, and then we solve differential equations by guessing. I think you heard that in your math course. And just a little digression. To show you just how much my social life was fun in grad school. In grad school, I solved a differential equation that hadn't been solved before. Okay? And I speak to you with that little accomplishment, trivial as it may be, under my belt, because I really did it exactly the way your teacher told you. I guessed solutions. And so I was doing this project, and part of the project in my derivations, I had experiments and I had a derivation going on, and I was able to trick down the derivation into a really nice differential equation that was it was actually a nonlinear differential equation, and so it hadn't really been solved before, but it was such a cute little equation that I carried it around with me in a notebook, a pencil, and an eraser. And I just carried these three things around with me for about 6 or 7 months up in Portland, Oregon. And yeah, I did all this other stuff. But when I went down and I sat by the river and I ate a peanut butter and jelly sandwich and I looked out at the boats and all the other people having fun, I took out my differential equation and I guessed solutions to it in a structured, careful manner, which I had degrees of freedom in. And it didn't surprise. It surprised me more than anybody else that one day it solved. One day I cracked it. So when they say you guess the solution to a differential equation, your guess in class is always right. But I want you to picture if you had a differential equation you've never seen before. This instant gratification business isn't going to cut it. You're going to be playing with this, tickling this, probing this, patiently, like an artist, teasing out the answer, and you may never come. So, having been there, I can attest to you that when they say guess, you really do guess. Of course, this is one that somebody else guessed at, and so I'm very very grateful for that particular guess because I can spend the time not guessing and boring you with my personal past stories. And so I have this nice exponential decay that you've seen a million times before. Okay. And so this is the voltage waveform that comes off of this resistor, and we solve this equation with a differential equation, and out comes the solution. So where does that voltage come from? And another way of thinking about it, another picture that's been drawn, is that I have some sort of initial condition on my capacitor. I charge up a capacitor, and then I throw the switch, and that capacitor, that charge bleeds across the resistance. I have to be a little careful. I have 15 more minutes? Ooh. Finish the problem, digress. Easy decision. Another part of my past was playing around with these guys, except now imagine that the capacitor is a bank of big oil can capacitors that might take up half of this class. Okay, so the capacitors that each one will hold off a kilovolt of voltage, and I wire them up together with wrenches and big braid of copper. You work on this circuit like you work on a car on one of those little one of those little things that you roll underneath it to crank on it. That's fun. So this piddly little picture here, let's think about this as a big array of these huge capacitors, these huge jerry can capacitors is what we called them back then. I'm not sure I know why, but maybe because of the oil cans, the gas tanks were the jerry cans. I don't know. But anyway, so to charge this mess, it stored a heck of a lot of energy. Remember 1/2 CV squared? So capacitor stored a heck of a lot of charge on this. Okay? So we'd have a piddly old DC power supply, not much bigger than what you have upstairs, and we would trickle charge the capacitor. So we'd keep the switch open, we'd throw the switch here, the charge would trickle in, we'd go off for lunch, we'd come back and it would be more or less charged, and then we'd throw the switch. So an hour of charging, throw the switch, a microsecond of time for that charge to come in there, and boy did we have fun. This thing ionized. The resistance was actually air, and so it ionized and became a very, very, very bright light source. It was really, it was fun. But that's when you really put your LRC circuits to the test, because a small move could really hurt people. so anyway, So where does that voltage come from? You charge that up, and the way we represent initial conditions, and I don't know if you've seen this before, or how much you've seen this before, or whether you're comfortable with this, but I'm going to write down my differential equation, and I'm going to represent that trickle charging as a delta function. So this role of this delta function is to establish the initial conditions on the capacitor. Okay? The role of that delta function is to establish the initial condition of the delta function. Okay? And so this guy is equal to infinity at time t equal to 0, and it's equal to 0 for all times greater than 0 plus. And what I mean, so if it's nothing, it charges up to some value of energy storage. At the moment I throw the switch, the spark gap, or the thyrotron switch of that big experiment I was talking about, I have a sudden rush of current, and beyond that, the forcing is over. Okay, so the role of delta function is to establish an initial condition. If I plot this, I have a V naught here. There's my initial condition. Right? There's my initial condition. And so this delta function, the strength of that delta function, and I need to have some units in there, right? So there needs to be something in there for strength. Units. I'll slough that off a little bit for now. But that V naught is sitting right in there with that delta function. And that's what gives rise to this guy here. And now let me pull this picture here. Now you can. So now what I'll do is I'll add there the same delta function that I'm doing there. So you start to get a sense of where I'm going with this. And so V of t is equal to H of t is equal to V naught e to the minus t over RC. Okay? So now I'm blending my differential equations with my signals and systems. I'm blending my differential equations by my initial conditions. The input to that RC circuit is a delta function, and then the response of that delta function is that V naught e to the minus t over RC, and we call that a delta function response, or H of t. Okay? If that's the case, then if I take my H of t and I Fourier transform it, then I'll get capital H of omega, right? So the impulse response, Fourier transformed, is that. It starts at 0, so I don't have to worry about minus infinity. Whoops, 0 to infinity, e to the minus t, 1 over RC plus I omega. Sorry again for the I instead of a J. I'm just having so much fun, I'm not paying attention. if I do that integral, I get that. And if I, this is a little sloppy, but you see that 1 over c there? I probably shouldn't have that c there, but I'm not going to stress too much about that, and I don't want you to stress.
Can you show the integral of this stuff?
Of course. Okay. So we solved the differential equation for h of t. We identified for the particular solution for a delta function. The particular solution for the delta function was the delta function response. Yes, I'm being sloppy about constants and stuff. I apologize, but that's just the way it is. The most important thing is this form of that denominator, where the omega is in that denominator. And there's my h of omega. Okay? Now, let's see. Or,
why did you cross out the C?
oh, I'm sorry.
You crossed out the C.
Do you see this I over c in here?
Yeah, okay.
I wouldn't stress too much about it. I'll make, in other words, I'll make the same mistake all the way through here. And I'm not, it's not that much of a mistake, really, because it's all scalable. Now, let's see, where was I? Oh, yes, okay. dv dt plus 1 over rc.
We can't see.
Okay. V is equal to I over c. Okay? Is that okay? Now what I'll do is I'll Fourier transform this equation. And so I'll have j omega, v of omega, plus 1 over rc, v of omega. And that's going to equal vn of omega over c. Okay? So v out over vn.
Why would that be Vn of omega?
That's the driving term.
I'm just wondering how you
Oh, the current, you mean?
current. Yeah, I'm just wondering how you looking at I. Okay.
Sorry. It's just what it's the forcing term. I'm sorry. I don't want to get too stressed out about current to voltage, transimpedances, and that kind of stuff. But the output over the input is equal to h of omega, and that's equal to 1 over c j omega plus 1 over rc, which is equal to rc times 1 over c, 1 plus j omega rc, or that's equal to r over 1 plus j omega rc. Okay? And the noteworthy thing about that is those guys are the same. Okay? Or I can Fourier transform the circuit so the R becomes an R, and the lumped impedance, or the complex impedance of the capacitor, is 1 over j omega c, and I have an R equivalent is equal to 1 over j omega c r over 1 over j omega c plus r. That's how you add up two impedances that are in parallel. Everyone okay with that? And again, that goes to R over 1 plus J omega RC. It's no accident that Fourier transforming the circuit and working with lumped impedances gets us to the answer a lot faster. Okay? There's no accident there. But my point is all this stuff gets you to exactly the same signals and systems answer. All this stuff gets you exactly to the same signals and systems answer. Okay? All right. Now, let's hold that thought for just a second. Oh, I guess one quick thing here. Help me out here. If let's just finesse the J for a little bit. Okay, if omega is equal to 0 or very small, this term is small relative to 1, and so I basically have a passive around a resistor. Okay, if omega gets big, then I can neglect 1. J goes upstairs, clear it out magnitude-wise. The R's cancel. And I have a much bigger denominator, which means my response is small. Okay? So, high pass filter, low pass filter. Okay, therefore it's a low pass filter, and that analysis is the same no matter what however we derive that, right? However we came up with that transfer function, the equivalent resistance or whatever, we got the same low pass filter behavior. Okay, in whatever course we were revisiting. Whatever course we revisited for that simple circuit, we got exactly the same thing. Okay. All right. I'm going to come back to that, but I want to spend a little bit of time. Talking about H of omega and filtering. Okay. I'm flashing, so I'm still a little bit alive here. So a filter will change the amplitude, and it will either increase it or decrease it of a selected set of frequencies. And it will shift the phase of a selected set of frequencies. That's what I've been telling you all along. All it does to a frequency component is shift the amplitude and the phase. Okay? All right, I think I'm off. Yeah. All right. So we're going to come back in 15 minutes. We're going to come back in 15 minutes, and I'll wrap this. I'll finish this discussion, and then we'll get into the modulator. And at least with I think we'll have just enough time to introduce what the modulator is, and to look at the modulation property in a little bit better shape, at least for a local oscillator.